Hello, welcome back to our online class. In this is the course AAA 351 or 352 Analog Principles of Communication Systems. In this we will cover the chapter 4 and the title of the chapter 4 is Amplitude Modulations and Demodulation. I am Dr. Zishan Kaleem from Comstate University Islamabad Wa Campus, EE Department. So let's start with our lecture contents. In this chapter we will cover several topics, but in this video specifically I will cover some contents because we will divide the lectures in this chapter into several lectures. So first of all, in this video we will cover what is modulation, and then what are the types of amplitude modulation and demodulation, and what is the double sideband suppressed carrier amplitude modulation, and how we demodulate the double sideband suppressed carrier. Okay, let's start with our first topic, which is the modulation. Modulation is the process that shifts the range of the frequencies. What does it mean? That usually whenever we generate the signal, it is called a baseband signal. We will discuss later on. So that baseband signal is of usually of very low frequency. So after doing modulation, we shift that from the lower frequency to the higher frequencies. What are the benefits of doing this? We have a reduced antenna size and we have a better usage of limited bandwidth. How better usage? In the sense of, because whenever we generate a signal in the low frequencies, then every signal usually generates in that same particular band. So by doing modulation, we can use the higher frequency bands as well. What are other benefits? It is robust to errors and distortions. There are numerous types of modulation. For example, analog modulation, uh, uh, it has amplitude modulation, and further types like DSB, SSB, VSB we will discuss in this chapter. And then in the next chapter, this is frequency modulation and delta modulation we will discuss later on. These are the types of analog modulation. In the sense of digital modulation, there are amplitude shift keying, frequency shift keying, and so on. And the final one is the pulse modulation, pulse code modulation, etc. So in this course, our major contents will be related to the analog modulation. So we will try to completely and fully discuss these topics. So these are the some examples of modulated signals. Like the FM radio, we usually listen at our homes or in the way. So these are the frequency. Like they starts from the 88 megahertz and goes towards 108 megahertz. And similarly, wireless LANs have a carrier frequency 2.4 or 5 gigahertz. So this is also a higher frequency. Cellular radio usually lies between 806 to 890 megahertz and so on. So we can say that in baseband communication uh, can't be transmitted over a radio link without modulation. So suitable for transmission over a pair of wires, coaxial cables, optical fibers, etc. So in communication that uses the modulation to shift the frequency spectrum of a signal is known as the carrier communication. So previously we discussed the baseband, and what is the carrier communication? When we shift the frequencies spectrum of a signal. So how we shift? We need to modify some parameters. So one of the basic parameters are we can say that amplitude, frequency, or phase. These three are the main parameters which we usually modify. So if the carrier signal amplitude is modified, then we call it as a amplitude modulation. And whenever the carrier signal frequency is modified, we call it as a frequency modulation. And similarly, whenever the angle is modified or the phase is modified, we call it the angle modulation or the phase modulation, PM. So these are the three main type of the modulation. So FM and the PM belong to the class of the modulation known as the angle modulation. So these two modulation like FM and the PM, we call that collectively called that or named that as the angle modulation. So modulation is used to transmit analog as well as the digital baseband signals. So what are the major types of amplitude modulation. As this chapter will only focus on the amplitude modulation, so we need to discuss what are the major types of the amplitude modulation. First of all is the double sideband suppressed carrier. Other one is the amplitude modulation. We called it simply the amplitude modulation or double sideband with carrier. Then the vestigial sideband modulation, quadrature amplitude modulation, and after modulating the signals, we need to detect or demodulate the signal. So there are two types of demodulation or detection. One is the coherent, the other is the non-coherent. We will discuss these terms and these schemes in detail. So what are the double sideband suppressed carrier modulations? Uh, Actually, this is the name given because of the double sideband suppressed carrier. These are the two terms. These this belongs to the amplitude modulation. In general, we can say that this is the one of the category of the amplitude modulation. But why we call it a double sideband and the suppressed carrier? The reason is that when we transmit, there are two sidebands, so we call it double sideband. And when we transmit the modulated signal, we don't transmit the carrier, so we called it as a suppressed carrier. So the terminology is that. So amplitude modulation is characterized by the fact that the amplitude of A, for example, the carrier is signal cos omega ct plus theta c, and the carrier amplitude is A, is varied in proportion to the baseband signal. So if you want to transmit the message signal mt at some distance, then this is the carrier signal AC or A cos omega ct theta c. So whenever you transmit this message signal, you will change the amplitude of the carrier. So that is why it is called amplitude modulation. The frequency here omega c and the phase here theta c are constant. It means that whenever you will modulate the signal using the message signal, then only the carrier will change and the rest of the things like the frequency part and the phase part will not change here. They will that will remain the constant. If the carrier amplitude is made directly proportional to the modulating signal, the modulated signal is mt cos omega ct. This type of modulation simply shifts the spectrum of the carrier frequency. So, for example, let's start how it works. For example, if mt is your message signal and this is the time domain signal, I will write it here, and this is the same signal but in the frequency domain. So I will name it as a mf domain. So mf, mt message in the time domain, mf message in the frequency domain, same message. So whenever you modulate, it means you multiply the two signals. This is your message number one, and this is your carrier number two. So you multiply these two. This is the time domain representation t, and we already proved that what is the frequency representation of this. In the last chapter, we already described. If you don't know, then please visit that lecture. So after taking Fourier transform, it means we are taking Fourier transform here, then we will get this. Okay, we'll get this result. So this is mt. So it means that after transmitting message signal on this carrier, we shifted the frequency of the message signal to that carrier frequency. For example, this is the message signal m. So there are two side bands, one at fc and the other at minus fc. So this is the frequency domain version of the mt cos omega ct. So let's start with the pictorial view and the block diagram. How the block diagram of double sideband suppressed carrier look like. So this is our message signal mt, which we call the modulating signal, and this is our carrier signal. We call it as a name. This is cos omega ct, and we named it as a carrier signal. So after passing through a modulated block diagram of the block, so it will get the mt cos omega ct, and we named it as a modulated signal. So this is our message signal in time domain, and similarly, if we do take the Fourier transform like in frequency domain, then this will be the similar signal in time domain will look like and that way in the frequency domain. and it occupies the bandwidth B. And so after modulating like MT into cos omega ct, we get the MT cos omega ct. So this is the time domain version of after multiplying this with the carrier. Here they didn't show how we achieve this one, so I would like to explain this as well. For example, you have a carrier signal which is a cosine with frequency like this one. It will be rough, so you can understand, I think. So after doing multiplication with this carrier, we got this one, right? So how we plot this? For example, this is the upper side, and to plot the same way in the lower side, you can go in that way, okay? And then fill this carrier inside that one. This and this. Sorry. Mm, This, so on. Okay. Here is not a clear, but from here you can see that you can notice that here the frequency of the signal carrier signal is not changing. Only the change is in the amplitude of the carrier. So that's why we call it as an amplitude modulation. So after getting this time domain signal, if we take the Fourier transform, so we will get this one. This is the Fourier transform of this one. Okay. It means that this is the modulated signal in Fourier domain. So how it looked like this is the carrier frequency. So it means that this message signal with amplitude 2A is shifted to the carrier frequency FC, and it occupies the bandwidth B, and here it will occupy the double up twice of the bandwidth. It is 2B. It is 2B. This bandwidth. And the portion from carrier to this part is called the upper sideband, and the portion from carrier to lower is called the lower sideband. And it will have image copies, so it is the lower frequency is called the lower sideband, and here it is called the upper sideband. So whenever this is generated, its image will also be generated. So this is the modulated signal after multiplying MT with the cos omega ct. So we note that the signal which we would like to modulate was the of the bandwidth B, but after modulation it is 2B hertz. We discussed the rule of getting this 2B hertz bandwidth in the last lecture, where I told you that whenever two signals multiply, then its bandwidth will be added. So bandwidth B becomes 2B hertz. We also observed that the modulated signal spectrum shifted at the omega c is composed of the two parts, omega c or fc. We will use these terms interchangeably in this lecture, but there is not much difference except the two pi terms. So there are two parts, omega c known as the upper sideband, and the portion below omega c is known as the lower sideband. And similarly, there is a reflection copy of that which centered at the minus omega c, and that also have upper and lower sideband. And the modulated signals in this scheme does not contain a discrete component of the carrier frequency. It is called double sideband suppressed carrier modulation. Why we call double sideband suppressed carrier? Because whenever we transmit the signal, we don't transmit the carrier independent carrier from beside the modulated signal. So, what are the conditions to accurately get the signal, modulated signal? For example, the figure shows, which we already seen in the last two slides. There is a carrier frequency that should be greater than 2B. For example, this is your modulating carrier frequency on which your modulating signal is transmitted. So the carrier frequency should be the greater than two times, greater or equal to two times of the bandwidth of the signal. Otherwise, there will be overlap and the information will be lost. If it is less, for example here, then the information which you would like to modulate MT is lost in the process of modulation. So you can't get back the exact copy of the message signal which you modulated at the transmitter side. So the next part is the double sideband suppressed carrier demodulation. What does demodulation mean? You transmitted the signal mt cos of omega ct. So now you transmitted your message signal on the carrier. So that is mt cos omega ct. So this was your message signal, desired signal, and this was a carrier signal. Carrier means, for example, you are going to other city, you usually use the car. So car would be your carrier, and the U would be the message signal. For example, U would be the message signal, or the human, any human can be a message signal, or any person riding on the car would be a message signal. So in the end, our target is to get that message signal back. The similar process is in the communication. You need to get back the message signal which you transmitted using the carrier. So how would you get back this signal? So that this process is known as the demodulation. So in communication, it means that with demodulation, double sideband suppressed carrier modulation translates or shifts the frequency spectrum to the left and right by omega c, as we already seen or discussed. The process of recovering. Now the process of recovering the signal, it means the message signal, from the modulated signal, it means this signal, the combined signal mt cos omega c, retranslating the spectrum to its original position. It means we transmitted it to a higher frequency, and we want to get back this message signal which lies in the lower frequency band. Is referred to as the demodulation or detection. They have a two name, demodulation or detection. If the modulated signal spectrum is shifted to the left and to the right, we obtain the desired baseband spectrum plus an unwanted spectrum to omega c or 2fc. Here we are using 2fc. The latter can be suppressed. So whenever we do this process of demodulation, what would happen? There will be a message signal plus there will be some other signal generated at the frequencies 2 times fc. Thus the demodulation is almost identical to modulation, which consists of multiplication of the incoming modulated signal. What we did in the modulation, we just multiply the message with the another carrier, like the carrier signal, this one, right? So to recover this signal, we also need to multiply mt cos omega ct, this is our modulated signal, with another carrier, right? Cos omega ct, omega ct. So we need to multiply with another carrier and then pass through a low pass filter. Let's look at the next slide. Here let's look again how it looks like. For example, this was your modulated signal M2 mt cos omega ct, and we need to get back this message signal out of this modulated signal. So this is demodulated block, and we again multiply the cos omega ct. Why we need to multiply again? As I told you, this is the double sideband suppressed carrier scheme. Suppressed carrier means whenever we transmit the modulated signal, this is our modulated signal, we don't separately transmit the another signal like cos omega ct beside that modulated signal. So we don't transmit this one with the modulated signal. So that's why we need this one to recover the modulated signal at the receiver side. So we multiply again this with this one, so we will get the E of t. We named it as a E of t, and then pass it to the through the low pass filter and finally get the half M of t. Like their amplitude will be reduced to the half as well. This is the spectrum, how it looks like. This is our message signal residing in the center, lower frequency, for example 0 to some B bandwidth, and this is twice of the frequency 2fc minus 2fc. So to remove this, our desired spectrum is this one. So to remove this, we will pass it to the low pass filter. This low pass filter. So what we get, the low pass filter will ignore these two non-desired signals, and finally we get half m of t. This is the mathematical representation of the demodulator. E of t, we named the last slide m of t cos omega ct into cos omega ct. So m of t cos square omega ct. So we will write is equal to half m of t. We can rewrite as using some trigonometric rules half mt plus mt cos 2 omega ct, because cos square omega ct can be 1 plus cos 2 theta over 2. Similarly, 1 plus cos 2 theta over this cos 2 theta over 2. So by using that identity, we rewrite in this way. So therefore, Fourier transform of the signal, if we take this Fourier transform of this signal, so half m of f, this one, and then you know that mt cos 2 omega ct, we already proved this one in the modulated part. So here instead of omega c, there is 2 omega c, so the frequency will be 2fc minus 2fc, and previously there was 1 2, and due to 1 half here again, so it will be 1/4. So we will get half mf 1 by 4 mf plus 2fc mf minus f 2fc. So this part is non-desired. We need to recover only this part. This is our message signal. So what we do? We will pass this E of f to the low pass filter, which will ignore this term, and we will get half m of f. But one thing you can notice from here, that we transmitted m of f, and in the end we got half m of f. So this is not desired. So how can we overcome this problem? This shows that the signal consists of two components. This I already explained. One is 2fc and minus plus 2fc. So we can get rid of this inconvenient fraction half in the output, like this one I was talking about, half in the output, by using a carrier 2 cos omega ct instead of cos omega ct. It means that when we are doing demodulation and multiplying with another carrier, so instead of multiplying only at the by cos omega ct, we have to multiply by 2 cos omega ct. So in this way, we will get the accurate result, like m of f only, not half m of f. So this method of recovering the baseband signal is called a synchronous detection or coherent detection. What does it mean? As I told you, when we are transmitting, when we are doing modulation, we are not separately or independently transmitting a carrier signal beside the modulated signal. So where we use a carrier of exactly the same frequency and phase as the carrier used for modulation. So as we are not transmitting the carrier beside separate independent carrier beside the modulated signal, so to detect that signal, we need to regenerate that carrier of exactly same phase and frequency. Okay, same phase and frequency. So this type of modulation where we generate the carrier at the receiver side of the same phase and frequency, this is called a synchronous detection or coherent detection. Thus for demodulation, we need to generate the local carrier at the receiver in frequency and phase coherence, means similar with the carrier used at the modulator. So this process is called coherent detection or synchronous detection. This is one example. Uh, this is our to demonstrate how the modulation double sideband suppressed carrier modulation works. For example, for a baseband signal, this is our message signal cos omega mt, or we can write as cos 2 pi fmt. So this is our baseband signal. It means that this is our message signal, which is also cosine, but we call it omega m or fm, the low frequency, and we need to find the double sideband suppressed carrier signal, sketch its spectrum, identify the upper and lower sidebands, and finally we need to verify that the double sideband suppressed carrier modulated signal can be demodulated by the demodulator in figure 4.1e. It means that 4.1e we use a synchronous detection or demodulator, so they desire that we should verify that this signal can be demodulated in the same way by using the coherent detection or coherent modulator. So solution, this problem is related to tone modulation. What does it mean by tone modulation? Tone modulation means that there is only a single frequency, like the modulating signal is a pure sinusoid. Sinusoid means there is only one frequency, not multiple frequencies, not harmonic. We don't have any harmonics. So there is a, it means that this message signal only has a one frequency component. So we called it as a tone modulation. Solution spectrum of the baseband signal is represented. So this message signal is a cos omega mt, We already proved that in the last lecture Fourier transform. That's why I told you this Fourier transforms are very much important. In the whole course, we will again use that Fourier transforms to represent the same signal in the frequency domain. So after taking the Fourier transform of this one, we will get half delta f minus f m f plus f m. It means that you can review that as well by going to the previous lectures. That cos omega m t, we have two impulses, one at frequency fm and other at minus fm with the half of amplitudes. So these terms here, what's the difference between this and this? This is in omega domain, like omega m, omega m. So we need to add pi as well to pi term. So by adding, multiplying by 2 pi, we will get the pi here. Okay, pi here. So let's move forward. In time domain, uh, how can we write signal? This is our message signal. It is called double sideband suppressed carrier message signal, and this is our carrier signal. This is the way how to perform the modulation. So in general, we write this one. So instead of general term, here we have a message given cos omega mt, and the carrier is cos omega ct. So we have a two cosine term. So after doing some algebraic manipulations or adjustments, we can get this half cos omega c plus omega m, half omega c minus omega m at t. This shows that if the baseband signal is fm, the modulated signal consists of two sinusoids. It means that if we have a baseband signal which is as a frequency omega m or fm, then we will get the two cosine signals, one with the frequency omega c plus fm and another will be omega c minus omega m. These are the diagrams, or we can say that pictorial view of the signal. This is our message signal which we need to transmit. As I discussed with you, that whenever we have a cos in the frequency domain, will have a frequency component, one at omega fm and one at the minus fm with the half amplitude. So this is the fm frequency domain version of the cos omega mt. So this is our cos omega mt. Right? I can't write neatly here, but it is a cos omega mt, and when we do the Fourier transform, then we will get this one. And this is the modulated signal double sideband spectrum. Like in the previous slide, we have two cosine signals. So one is at the fc plus fm, and other at fc minus fm, right? With the amplitude 1 4 1 4, and this is their upper sideband, this is lower sideband. Similarly, upper sideband and the lower sideband. So we need, whenever we demodulate, which will be on other side, so on the other slide. So in demodulation, we need this message, and we need to suppress by low pass filter. So these terms will be suppressed after passing to the filters, so it will be cancelled out. Let's see on the next slide. So this is the demodulation part. This is was your message signal. So on cos omega mt, so we need to multiply with another carrier, cos omega ct into cos omega ct. Similarly, so cos square ct omega ct is rewriting as using some algebraic expressions. Will get this one. The spectrum of the term cos omega mt, cos is centered at 2fc. So they are centered at 2fc and will be suppressed by the low pass filter, yielding 1 by 2 pass. So after passing this signal to the low pass filter, we will get the desired term, which is cos omega t. Thank you for listening. This was the first part of our amplitude modulation chapter, and the topic was double sideband suppressed carrier modulation and demodulation. So we will discuss further on in the next videos. Thank you very much.